Good day. I welcome you at the lecture on unit load method under the subject of Structure Analysis 1. The subject code is CEPC 503 and the related module number is 3. Myself Sandeepan Saha, Assistant Professor for the Department of Civil Engineering, Greater Kolkata College of Engineering and Management under JIS Group. Let us first have a look on the topics that we are going to cover in this lecture session. So topics are, that is the introduction to unit load method, theory of unit load method, and numerical examples. So what is basically a unit load method? This method is also referred as method of virtual work, which was developed by John Bernoulli in 1770. This method is used to determine the slope and deflection at a specific point of a beam, frame, or truss. In this method, a virtual unit load is applied at the point of deflection and in the direction of deflection, whereas a unit virtual moment is applied at the point of desired slope to calculate the slope. So basically, in this method, a virtual unit load is applied at that particular point where the deflection is required. So how do we apply this unit load method? In this method, the basic theory is, by applying the principle of work and energy, we get external virtual work equals to internal virtual work, whereas del is the internal virtual work and the external virtual work equals to 1 kilonewton into delta, where 1 kilonewton is the unit load and del is the internal virtual work. So basically, external virtual work is the multiplication of unit load and internal virtual work. And based on the internal virtual work for different types of loading, in case of different types of deflection, formula is given as follows. That is, del equals to 1 by EI integration 0 to L capital M into small m into dx, where capital M is the bending moment at x due to the actual loading, small m equals to the bending moment at x due to virtual unit loading applied at the point of deflection, capital L equals to the span of the member, E equals to the modulus of elasticity of the beam material, and I is the moment of inertia of the beam section. Now let us do a numerical problem using unit load method. In this problem, we have to determine the deflection at the free end of the following overhanging beam as shown in the figure. So we have the free end at point C, that is here. The given load is 45 kilonewton per meter, which is a UDL, that is uniformly distributed load, from point A to point C, that is up to here. The length of the beam from point A to up to point B is 6 meter, and the length of segment BC, that is from B to point C, the length is 2 meter. For this segment, that is from A to B, that is from A to B, the moment of inertia is 2I0, and from B, that is from here to up to point C, that is here, the moment of inertia is I0. Now we have to calculate the deflection at point C. That means we have to calculate del C, and in order to do so, first we have to calculate the reaction at point A and reaction at point B. In this problem, we are calculating the deflection at point C. To do so, there are certain number of steps that we need to do? So step number 1, we have to calculate the reaction at point A, that is RA, that we have to calculate, and reaction at point B, that is we have to calculate RB. So the step number 1 is calculation of RA and RB. So to calculate the RA and RB, we are taking summation of all moments about point A, that is equals to 0, as at point A the support is hinge support. So taking the summation of moment equals to 0, we have RB into 6 equals to 45 into 8 into 4. Solving this, we get RB equals to 240 kilonewton. Total RA plus RB equals to 45 into 8. That is, we have 360 kilonewton. So we have RA equals to 360 minus RB. As we have already calculated RB, that is 240 kilonewton. So we have 360 minus 240. We have 120 kilonewton. So the reaction force at A is 120 kilonewton, and at B the reaction force is 240 kilonewton. The next step is calculation of RA and RB based on a unit load acting at point C. So the step number 2 is calculation of RA and RB with respect to the 1 kilonewton force, that is the unit load acting at point C. To do so, again we are taking moment about point A equals to 0, that as the point A has a hinge support. So we have summation of all moments about point A equals to 0. We have RB into 6 equals to 1 into 8. From this we get RB equals to 8 by 6. So we have RB equals to 1.33 kilonewton. So RB equals to 1.33 kilonewton. So we get RB equals to 1.33 kilonewton, and we have RA plus RB equals to 1 kilonewton, from which we get RA equals to 1 minus 1.33, as RB equals to 1.33 kilonewton. So we get R equals to minus 0.33 kilonewton. So here we can see by calculation RA is minus 0.33. That means RA is acting in the downward direction, not in the upward direction. So from calculation we get RA equals to 0.33 kilonewton, and the negative, that is this, that is the negative sign shows that the RA is acting in the downward direction. In this step, we have calculated the reaction at A and B, that is RA equals to 0.33 kilonewton and RB equals to 1.33 kilonewton with respect to a unit load, that is this one acting at point C. This means we have to put a unit load at that particular point where we will be determining the required deflection as per the given problem. Here, the deflection is required at point C. So, the unit load, that is this one, is put at point C, that is here. Again, I am mentioning the unit load. The unit load is acting at point C, as the deflection is required at point C as per the given problem. And the reaction forces are calculated as per the unit load, that is 1 kilonewton acting at point C, that is the free end at point C. So the next step is, that is step number 3, which is calculation of bending moment at different portions of the member. So we have this member from A to C and the loading is 45 kilonewton per meter. To calculate the bending moment expressions, let's take a section XX, which is situated at a x distance from support A. So the expression of bending moment for the segment AB, that is M, with respect to section XX, we have 120x minus half into 45x square. So the bending moment for the segment AB equals to 120x minus half into 45x square. Now, to calculate the bending moment for the segment BC, let us take a section XX, which is situated at a distance x from the point C. So the distance between section XX and the point C is x. So the expression of bending moment for the segment BC with respect to the section XX, we have M equals to minus half into 45x square. We have calculated these expressions of bending moment taking sagging moment as positive and hogging moment as negative. Now, the next step is to calculate the bending moment expressions for different portions of the member for the unit load condition, that is this condition we are talking about. So to do so, let us take a section XX, which is situated at a distance x from A point. So the expression of bending moment for the segment AB with respect to the section XX, we have M equals to minus 1 by 3 into x. Now let us put the XX section at a distance x from the point C, and the expression of the bending moment for the segment BC with respect to the section XX, we have m equals to minus 1 into x. Here we have taken sagging moment as positive and hogging moment as negative. So this is the calculation table that we have already determined the expressions of bending moments for various portions of the member. The portions are AB and BC. Whereas capital M deals with the expression of bending moments for the original loading condition. That means this loading condition. And the expressions are 1 and 2. So these are the two expressions for the bending moment of the original loading condition. And small m deals with the expression of bending moment for the condition of unit loading. That means this loading condition. And the related bending moment expressions are as follows. That is this one and this one. The length of the AB portion is 6 meter and length of the BC portion is 2 meter. All these calculations that we have done will be put in this formula. That means we are talking about this particular formula. This formula will be used to calculate the deflection at point C, that is del C equals to integration of capital N into small m by EI into Tx, whereas m comes from this calculation table and small m, the values of small m will be coming from this calculation table, and putting all the values here we will get the deflection at point C. So now let us do the calculation as per this particular formula. Now we are going to calculate the deflection at point C, that is del C equals to integration limit 0 to L capital M into small m by EI Tx. So this formula will be used to calculate the deflection at point C, where the capital M, that is this one, and the small m, this one. As we have already derived the expressions of capital M and small m, and the detailed discussion of the calculation process of bending moment expressions are already done. So putting the expressions of capital M and small m into this equation, we get del C, that is deflection at C, equals to integration 0 to 6 120 x minus 22.5 x square into minus 0.33 x into dx by 2 EI 0, as the value of moment of inertia for the portion AB is 2I0, plus integration of limit 0 to 2 minus 22.5 x square into minus x into dx by E into I0, as the moment of inertia for the portion of BC is I0. Here this, this and these values that we have got from the calculations of various bending moment expressions. So this particular portion of this calculation deals with the details of AB portion of the member, and this portion of the calculation process deals with the details of BC portion of the member. So putting the details of portion AB and portion BC, we get, and upon further calculation, we get the deflection at point C equals to minus 135 by EI0. Here, negative value means that the deflection is occurring in the upward direction. So we have the deflection at point C equals to 135 by EI0, which is happening in the upward direction. In this calculation, that means we have applied the rules of integration process, and we get the deflection at C, that is deflection at point C equals to 135 by EI0, which is occurring in the upward direction. Thank you.